The next topic is logarithmic differentiation. There are two types of logarithmic differentiation, and one is large product and quotient like 3.1a and b, and a function with x expression in both the base and the power, like this: x to the log of x power, log of x to the cosine of x power. Both the base and the power have x expressions. Now, logarithmic differentiation, so we're going to have to use some log rules. So let me remind you of the log rule. Log of a times b was log of a plus log of b, and that's rule number 1. Log of a divided by b is log of a minus log of b, and that's the second log rule. And finally, log of a to the certain k power is the same as k times log of a. That's the third log rule. I'm not going to talk about the derivations of these. If you're interested, please go ahead and read some college algebra or trigonometry. Not trigonometry, excuse me, college algebra or pre-calculus textbooks. Okay, here we go. First type of problem, how do we handle y is equal to this big expression? In that case, we begin with taking the logarithm of both sides. Now, the logarithm in the right hand side can be simplified because this product can become addition, and then this quotient will become subtraction. So we have log of exponential of x plus log of x plus e, x plus 2 to the third power, minus log of x squared plus 1 to the fourth power, minus log of 3x minus 1 to the fourth power. Are you with me here? Everything in numerator become positive, everything in denominator become negative. Basically, we are using this rule and this rule at the same time. Rule 1 and rule 2 at the same time. By the way, let me write it down in the second line. This is getting a bit too big. And let's simplify this thing just a little bit. Now log and exponential cancel each other out, so that's x, and that's simple. Next, this 3 comes out as coefficient by the third log rule. And this power over here comes out as coefficient as before, and then one more. The power come out as coefficient. Here we apply the derivative. Here we apply the implicit differentiation. We take the derivative, but we use the implicit differentiation. What is the derivative of log of y? It's 1 over y, but by chain rule you have to multiply the derivative of the inside, y prime. So we get y prime of y equals to the derivative of this expression here. Shall we go ahead and take the derivative here one by one? Okay, let's go ahead and do that. Oops. Okay, what is derivative of x? That's 1. So far so good. What is the derivative of this log of x plus 2? It is 1 over x plus 2. Multiply the derivative of the inside, that's just 1, so we don't have to do anything here. Next, derivative of this, so it's 1 over x squared plus 1, but by chain rule we have to multiply the derivative of the inside. That's 2x. How about this one? Multiply the derivative of the outside is 1 over 3x minus 1, and multiply the derivative of the inside. That's 3. So let's simplify this a little bit. Okay, flip this y to the other side, and then we have this expression here. And we can simplify this in just a little bit, right? Multiply 3 here. Multiply 4 there, so that's 8 now. And multiply 4 there, that's 12. Almost there. We are looking for y prime, and we got y prime. But what is y? Well, given right here, isn't it? So copy this entire thing over here, and that concludes the differentiation. The derivative of this is this original y times this part, which was obtained from logarithmic differentiation. Take the log of both sides, simplify using the log rules, take the derivatives implicitly, and then move y to the other side. This kind of technique is called logarithmic differentiation. You can do the same thing to this problem as well, but I'm going to leave that as an exercise. No, let me change my mind. Let's do it. Let's do it. By the way, if you open it up, we have the solution here. Take the log, simplify, differentiate implicitly, and then flip the denominator, flip this denominator y to the other side, and then a final answer. It's all here. Let's do this. Okay. As usual, take the log of both sides. Log of y is log of this big expression, but square root is 1/2 power, so we just flip it over. And then 1/2 comes out as coefficient by the log rule. Okay, and then we can simplify this big expression here. Everything in numerator plus everything in denominator minus. So this is what we get. Plus plus minus minus. Simplify just a little bit further. Exponential and log cancel out, so we have 1/2 of x. And then 4 comes out, and we have the simpler coefficient. 5 comes out, and we have 5/2 here. 3 comes out, and we have 3/2 power. So here's the simplification. Now we take the derivative implicitly. Log of y becomes y prime over y. And then the derivative here, well, we just take the derivatives. Whatever inside the log goes to denominator and multiply the derivative of the inside. That's why we get this 2 and this negative sign, and then 9x squared. Actually 3x squared, and this 3 was there before. Maybe I should have written like that. 3 and 3x squared like that. And flip denominator over to the other side. Well, that's what we get. We did a little bit of simplification. Negative cancel out, sine of a cosinus tangent, but this kind of simplification is not really necessary as far as I'm concerned. And then rewriting whatever y expression that was given before, we get the final answer. There you go. Take the log, simplify using the log rule. Take the derivative implicitly, flip denominator to the other side, and then rewrite y as the original expression. Now, do you like this method? Well, I certainly don't. I'd much prefer to use an alternative method, which is generalized product rule. Goes kind of like this. Okay, goes kind of like this. This whole thing can be written as y as a times b over c times d form, and it can be written as a times b times c to the negative first power d to the negative first power, kind of like that. And then we apply the generalized product rule. The derivative of first function, the other will stay the same. Derivative of the second function and the others will stay the same. Derivative of the third function, the others will stay the same. And derivative of the fourth function, the others will stay the same. And here it is. Express all those as a big product, and then we just write everything in the product form. The red part are the derivatives, the black part just copying, staying the same. This problem 2, we can use generalized product rule here. Passing this 1/2 power to the power, we get the product of these 4 expressions, and then apply the generalized product rule. This is a derivative. I'm highlighting in blue. Now the second factor is the derivative. Now the third factor is the derivative. And finally, the fourth factor is the derivative. This is perfectly fine, but I took one extra step simplifying, which is totally unnecessary. This is perfectly fine. So which method do you prefer? Personally, I prefer generalized product rule, but our textbook uses the logarithmic differentiation. Looks like the other logarithmic differentiation has to be covered in a separate video. We'll do that.